I want to start today by looking at the absolute pinnacle of human engineering. Think of a skyscraper, the Burj Khalifa.
Or even something tiny, like a high-end GPU.
Exactly, like an H100. These are just masterpieces of design. We have these blueprints that are so detailed, they specify the position of every single steel beam, every transistor.
It's a completely top-down, meticulously architected process.
It is. It's the definition of intelligent design, right?
Okay.
You have a master architect who decides exactly where every single piece goes before anything is even built.
And that's effectively how we've been building AI.
Yes, we act like architects. We say,
Yeah.
okay, this model needs 50 layers, and layer 10 connects to layer 11 with this specific setting. We build these huge static structures.
And we just pour data through them.
Yeah.
But that is not how real intelligence is built. Not even close.
Not at all. And that's the realization that really hit me reading today's paper. Nature doesn't have a blueprint.
No. If you looked inside a human embryo at the single-cell stage, you're not going to find a tiny map saying neuron 4 billion goes right here.
No, you find a set of instructions. You start with one cell. It divides, it
Right.
specializes. And somehow, through this messy, sort of self-organizing process, you get a brain.
A brain with 100 trillion connections that can, write symphonies.
So the question on the table today is, what if we stopped building AI like skyscrapers and started growing it like embryos?
It's a fundamental shift in thinking. We're moving from the era of the architect to the era of, say, the gardener.
I love that framing. So we are doing a deep dive into this fascinating paper. It's called Towards Self-Assembling Artificial Neural Networks Through Neural Developmental Program.
It's from the IT University of Copenhagen, led by Elias Najaro and his team.
And their mission is, well, it's pretty audacious. They aren't trying to design a better neural network.
No, they're trying to design a code that grows a neural network for them.
To really get why this is such a big deal, we have to talk about something called the genomic bottleneck. I know you love this concept.
No, absolutely. It's one of the most elegant constraints in all of biology.
So let's just run the numbers because they are staggering. A human brain has roughly 100 trillion connections. That's the wiring.
But the human genome, the DNA that's supposed to have all the instructions, only has about 30,000 active genes.
Right. And you could argue a lot of those aren't even for the brain.
Exactly. So you've got, 30,000 lines of code trying to describe 100 trillion connection points.
It's a compression ratio that's just, it's mathematically impossible for the DNA to be a blueprint. It just can't store the location of every single wire.
Which means the DNA must be storing something else entirely.
It's not the structure.
It's the rules for growth. It's a generative algorithm.
That's a perfect way to put it. It's like the difference between giving someone a map of New York City that lists every single brick
Versus giving them a rule book that says, okay, commercial districts need wide roads and parks should be near houses, and then just letting the city build itself.
And that word reuse is so important. This paper is trying to replicate that same efficiency. They call their version the Neural Developmental Program, or NDP.
That's the artificial DNA.
Yeah.
And unlike a normal neural network where the intelligence is in the final weights, here, the intelligence is in that rule book.
The NDP that builds the network.
Exactly.
Okay, so let's get a little technical for a second, because the mechanism here is pretty wild. The grower itself is actually a neural network, right?
Yes, and this is where it gets a bit Inception-like. The NDP is a small neural network, but think of it as the code running inside every single cell.
So in their experiments, they start with a seed.
Usually just a single node, a single digital neuron just floating in a void.
Okay, so I'm that first neuron. I'm the seed. I've got this NDP code inside me. What do I do?
Well, you have to make a decision. The process runs in these loops they call developmental cycles. First, you look at your internal state, your embedding.
Right, embedding. It's one of those AI terms. For you listening, think of it like an internal passport. It's just a list of numbers that describes who I am and what's happening around me.
A perfect description. It's your local identity. So you, the neuron, you feed this passport data into your NDP, and it spits out a decision. The first one is, should I replicate?
Am I ready to be a parent?
Essentially, yes. If the NDP says yes, you spawn a new node. Now there are two of you.
And crucially, the new node gets an exact copy of the same NDP.
That is the most important part. Every single neuron runs the exact same code. There is no central brain, no foreman on the construction site. It's all distributed.
Which is just how biology works. My liver cells have no idea what my brain cells are doing.
They just follow local rules. So back to the cycle. You've replicated, now you have a neighbor. Step 2 is connection. The NDP decides, how do I wire this new thing up?
And step 3?
Waiting. Not all connections are equal, so the NDP assigns a weight to that new connection.
Yeah.
And then the cycle just repeats. Replicate, connect, wait, over and over.
And from that simple loop, running locally in every node, you get a complex structure that just emerges.
You do. And the researchers tested two very different ways to teach this NDP how to grow a good brain. Because it starts out totally random.
You have to train the gardener. So they used an evolutionary approach and a gradient-based one. Let's start with the evolutionary one. It seems more intuitive.
It is. It's basically survival of the fittest.
Mm.
Imagine you create 100 random NDPs. You let them all grow brains. Then you test those brains, maybe by playing a video game.
Most of them are probably useless.
Most of them do absolutely nothing, but maybe one of them twitches in the right direction,
Sure.
so you keep that one, you delete the failures, and you make slightly mutated copies of the winner.
And you just do that for thousands of generations.
Exactly. It's brute force, but it's very flexible.
But the second method, the gradient-based approach, that's the heavy hitter in modern AI. That's backpropagation.
Right. And this is much harder, technically. Backpropagation is basically calculus. You're finding the slope of the error to figure out how to get better.
But how do you use calculus on a graph that's changing size and shape? That sounds like a nightmare.
It is tricky. They had to use a specific technique, PPO,
Yeah.
and they had to constrain the growth a little.
Yeah.
They forced it into a feed-forward structure, so information only flows one way.
So it's less wild and organic than the evolutionary way.
A bit less, but it's much faster, more sample efficient.
Okay, so we have the theory, we have the grower code, but the big question is, does it actually work? Can you plant a seed and get a brain that solves a problem?
Or you just get a digital tumor.
Hey! Right, which we'll get to.
But yes, generally it works. They started with the Hello World of AI, the XOR gate.
A simple logic puzzle.
And the evolutionary NDP grew a tiny graph, just 4 nodes, 7 connections, that solved it perfectly.
Okay, before nodes is easy. Let's talk about carpol, the balancing a stick test.
This was impressive. It started with a single node. Over just 4 growth cycles, it expanded into a network of 10 neurons and 33 edges.
And the performance.
Perfect score.
Yep.
500 out of 500. Solves it completely. And remember, the researchers didn't tell it you need 10 neurons.
The NDP figured that out on its own.
It decided that 10 neurons was the optimal complexity for that specific task.
That's the aha moment for me. The architecture is adaptive.
Well, theoretically.
Yeah.
Which brings us to Lunar Lander, where things got a bit messy.
Lunar Lander is much harder. You're landing a spaceship, but the terrain is randomly generated every time.
It's stochastic. The world changes. And here, the grown brains really struggled. The network grew to about 16 nodes. It got a mean reward of 116.
Is 116 any good?
It's passable.
Mm-hmm.
200 is considered solved, but the real problem was the variance. The standard deviation was plus or minus 124.
Whoa, so sometimes it lands like a pro and other times it just smashes into a mountain.
Exactly. It was unstable. It highlights a real vulnerability here. It struggled to find a single growth pattern that worked for every possible terrain.
Okay, so it has trouble with randomness, but they did have a big win with the gradient-based approach on MNIST, right? And that's not a physics game, that's handwriting recognition.
Yes, a classification task.
Yeah.
You're dealing with 8 by 8 pixel images of numbers.
And that usually takes a pretty big network.
Relatively, yeah. Here, the seed grew into a network of about 106 nodes, and it achieved 91% accuracy.
91% isn't a world record, but it proves the point.
It proves scalability. It shows this growth mechanism isn't just a gimmick for logic gates. It can handle high-dimensional inputs, like vision.
Now, speaking of mimicking nature, there was one experiment that I found absolutely fascinating. It wasn't about solving a game at all. It was about the geometry of the brain.
Ah, yes. The small world experiment.
So I know small world networks from social science, like the 6 degrees of Kevin Bacon idea.
Precisely. In graph theory, it means you have high clustering, your friends know each other, but also a short path length to get from one side of the network to the other.
And biological brains are wired exactly like that. It's super efficient.
Right. So the researchers asked, can we train an NDP not to solve a task, but just to grow a graph that looks like a biological brain?
And could it?
It worked beautifully. The NDP grew a graph with a sigma value of about 1.27.
What does 1.27 mean for us?
In this context, anything greater than 1 is considered to have small world properties. It proves that this local growth mechanism can spontaneously organize into the same efficient structures we see in nature.
That is profound. We're kind of reverse engineering the geometry of thought, but
Yeah.
we have to be realistic. What are the other limitations here?
The biggest one, ironically, is knowing when to stop growing.
The stop button.
Yeah. In biology, your brain grows rapidly and then it stabilizes. In these experiments, they noticed a worrying trend. Performance would peak, say, at 37 nodes for Lunar Lander with a score of 130.
But it kept adding neurons.
It kept adding them. It got up to 77 nodes, and the reward dropped down to 110.
So it actually got dumber as it got bigger.
Exactly. This is the digital tumor problem. More brain isn't always better. You're just adding noise and overfitting. The current NDPs really struggle to learn a stop condition.
That seems like a pretty critical flaw. You can't have your AI just growing until it crashes the server.
It's a major challenge. And the other big limitation is the lack of nurture.
Nature versus nurture.
Right. Right now, these NDPs are pure genetics. The growth is all predetermined. But in your brain, if you learn to play the piano, the part of your brain controlling your fingers physically changes. It gets denser.
Activity-dependent plasticity. Use it or lose it.
Exactly. These NDPs don't have that yet.
Yeah.
The experience of solving the task doesn't feed back to change the architecture in real time.
So we have a system that mimics nature's compression. It can grow solutions, but it doesn't know when to stop, and it doesn't really learn from experience, architecturally speaking. Why does this matter right now?
I think there are two massive implications. The first is compression. We're in the age of trillion-parameter models. Storing these things, sharing them. It's a nightmare.
Right, you can't download GPT-5 onto your smartphone.
But with this method,
Yeah.
you wouldn't need to. You just ship the seed. You send the tiny NDP a few kilobytes of code, and the phone grows the massive brain locally. It's the ultimate zip file.
You send the DNA, and the recipient grows the organism.
Precisely. And the second implication is robustness, which leads to your provocative thought about healing.
Yes. This is where my mind went. If I have an AI built like a skyscraper and I cut a power line, the whole thing goes dark.
It's fragile, but biological systems are anti-fragile. You got to cut your skin heals.
So if we're running a mission-critical AI, say on a Mars rover, and a cosmic ray hits the chip and wipes out a cluster of digital neurons.
In a standard AI, that's a fatal error. Game over.
But in a grown AI...
Well, if the NDP is constantly running in the background, the neighboring neurons would notice the silence. They'd realize, hey, there's a gap here.
And the local rules would just trigger a new growth cycle.
They could spawn replacements, rewire around the damage. You could, theoretically, build self-repairing AI.
Mortal code.
Potentially.
That is a future that is both incredibly exciting and, I'll be honest, a little bit terrifying.
Yeah.
But it feels like a necessary next step.
I agree. We're moving from static engineering to dynamic biology. It turns out the best way to build a brain might not be to build it at all,
but to let it build itself. From architects to gardeners, I love it. We will put a link to the paper in the show notes for anyone who wants to dig in.
It's definitely worth a read.
Thanks for diving in with us.
Always a pleasure.